Hey, welcome everybody. Coffee with Caleffi. Thanks for tuning in today. I'm Bob Hot Rod Roar. I'm going to do the intro and a couple housekeeping slides here, and then we're going to turn it over to John. And we're delighted to have John, as always. Everybody gets a lot smarter when we spend some time with Siggy, so I think you're going to enjoy this presentation today. So, yeah, a couple housekeeping slides here quickly. If for some reason we're not coming through clear or it's jumpy or something like that, just log out and log back in. Most of the time, a new connection fixes little glitches like that. At the end of the presentation, there'll be a survey, and if you fill that out, you can request the slides, the whole presentation that we'll send off to you. So, and yeah, you can listen to it. It'll probably take us maybe a couple days to a week to get it up on our YouTube channel, but you can listen to it again or share it with your colleagues if you'd like to. Okay. So that's a certificate that you get if you fill out the survey at the end. We don't have this registered with anybody officially, but for the most part, we found if you send those in, they'll accept that as some training hours for your license requirements. Okay. Yep. Number 35 is on the street. We're working on the next issue of Hydronics. Hopefully you're getting those in the mail. If you want the hard copy, sometimes we redo the list every now and then. If you've fallen off and you're not receiving the hard copies, just go back in and sign up again. But you can get them mailed to you. We also have them online as a PDF, or you can also do a virtual book now where you can just page through it. So that information is available a number of different ways now. Okay, our next presenter for next month from Ray Hall is going to be talking about system design and balancing. So that'll be another interesting one. Make sure you get that one on your calendar. And there's our guy right there. There's John. So he's the voice you're going to be hearing for the next little bit. So I'm going to help with questions, and any questions that we don't get to through the presentation, we do email you, and we won't let anybody slip through the cracks there as far as questions. So I think that's probably it on housekeeping.
Yep.
Yep.
Okay. Well, thanks, Bob, and Max. Thanks for the intro. And we're going to go through a new topic today. As we've done different issues of hydronics over the years, many times we stop and we think, gee, we've covered so many different topics within the field. What haven't we covered? What would be of interest? What would be of practical application, especially residential light commercial systems? And of course, right now, the hydronics industry is transitioning along with a lot of other industries. We're seeing more interest in heat pumps, both air to water, geothermal, water to water, and of course, not to leave out modulated condensing boilers. But in general, we're seeing higher efficiency heat sources and lower operating temperatures. So one practical question would be, let's say somebody has an existing hydronic system. Maybe it has thin tube baseboard, maybe it has cast iron radiators in it, fan coils. Maybe it's been operating at relatively high temperatures, like 180 to 200 degree Fahrenheit water. And somebody's interested in installing perhaps a heat pump or a ModCon boiler. But the question comes up, well, how well will that existing circuit perform if I reduce the water temperature from, let's say, 180 down to 120 degrees? And of course, you can guess at that, and there are some theoretical ways to approach that. But this session, and Hydronics 35 is definitely the companion to this session. This is about how can we, with a reasonable budget and reasonable equipment, how can we monitor the performance of a system and use that data that we collect to project how that system will work at different temperatures. So, the question might come up, well, why should I bother to evaluate the performance? Why don't I just drop that heat pump into that system, take out the boiler or just put it parallel with the boiler, operate it and see, just kind of guesstimate how well it's going to work. Well, let me give you the analogy to that. Let's say you want to get involved in Formula One racing and you start out with a really high performance energy source like this Ferrari engine here. They're about $500,000 now from what I understand. but you install it in this, a 1957 Chevrolet. And some of you recognize that symbol there does not equal this, a Formula One racer. So obviously we've got a poor match between the power source, the energy source, and what I'll refer to as the balance of system. In this case, it would be the body, the transmission, and so forth in that 57 Chevrolet. We've got a very poor matching there. So the analogy to that in a hydronic context would be, here's an air to water heat pump, and this will perform better at lower water temperatures. These systems have been doing some work on these systems throughout New England, and we're seeing some really encouraging performance with these in terms of coefficient of performance. But that performance is very tightly linked to the water temperature in the system. So let's say we take this very contemporary, state-of-the-art heat source, and we combine it with something like this. This is kind of from my Wall of Shame collection here, PEX tubing stapled to the bottom of the subfloor, to the side of the floor trusses, or even Reynolds wrap here being used for heat transfer plates. I don't think anybody would disagree. This is a very poorly designed, poorly thought out distribution system. So again, it's just like putting that Ferrari engine in the 57 Chevrolet. We're not going to win first prize or get superior comfort from that. So instead, we're probably going to get finger pointing, high bills from the customers, not a good way to introduce, especially a contemporary heat source that's relatively new in the market. So again, this probably seems like common sense, but I always like to stress it. When you have an opportunity to put in a high performance heat source, don't assume that you can simply drop it into whatever is there without evaluating it and expecting it to perform well. Dropping a new heat source is not going to fix existing problems. And we have found a lot of the issues when these types of heat sources are going into systems. It's not necessarily that the new heat source isn't performing properly, but it is oftentimes, it's just poorly matched to that distribution system, both hydraulically as well as thermally. So again, this is kind of the background why we wanted to develop material on practical ways to evaluate the performance of the system and then make a determination how well will that system perform with that new heat source. And there's a couple ways that you can do this. One is theoretical. And I enjoy this. In a theoretical approach, you're going to be looking at the hydraulics of the system, and you're also going to be looking at the thermal characteristics of the system. And like modeling most physical entities, it really requires a lot of input. You have to go to the site, and you literally have to catalog what is there. How much piping, what size piping, how many fittings, what type of fittings, valves, what is the circulator or multiple circulators in the system, what are the heat emitters, what are even the fluids, because the fluid properties are going to affect the flow rate. The flow rate is going to affect the heat transfer. So this requires a lot of on-site time, and it also requires a lot of calculations. And those calculations can be processed through a computer. Computational speed isn't any problem, but it also relies on the theoretical model of every component, be it a circulator, a pipe, a heat source, anything. So if we have a circulator, for example, we can look up the published pump curve for that circulator. We have to assume that the circulator that's in the system, and it might be 10 years old, it might be 15, 20 years old, but we have to assume that the circulator is operating on the pump curve that's published for that particular make and model of circulator. We have no way to necessarily independently verify that, short of taking the circulator out, putting it in some type of a test apparatus, and running. And the same holds true for all the other components in the system. Is the baseboard, for example, performing based on its published performance? Or Are the fins bent? Is there dust in there? Is there, debris that is somehow impairing the performance of it? So theoretical modeling is a way to approach it. And it probably is going to get you in the ballpark, but it's not necessarily going to pick up on all the nuances in the system. Whereas measured performance is going to do that. It is going to require some on-site work, not as much cataloging, not as much taking inventory of what is out there, because you're actually going to measure flow rates, you're going to measure temperature differences, as opposed to trying to come up with all that theoretically. And you're going to capture effects that you wouldn't necessarily capture, like maybe the circulator isn't operating exactly on its pump curve. Or maybe there's some piping in an area of the building you just can't access. You just can't see what's there. And perhaps you didn't include that in your theoretical model. So we're going to focus on the measured performance and looking at what kind of instrumentation is both practical and affordable to do that. There are some calculations, but they're pretty simple calculations. So again, the results will be based on the actual combined performance, both hydraulically and thermally, rather than what the theoretical or the rated component performance models are. So when we measure the performance of a circuit, and here's a simple system, a boiler with a couple zone circulators and a couple circuits there. I'm just showing a hypothetical model. You could have more baseboards, you could have more zones and so forth. But there's two things that we need to evaluate in order to get the thermal performance, okay? And many of you know that. And one of them is temperature drop. What is the temperature drop from the beginning of the circuit to the end of the circuit? What is the delta T of that circuit? Okay. And we need to combine that with the flow rate in that circuit. Okay. A flow rate definitely has an effect on performance. As the flow rate in a circuit goes up, you get better heat transfer because you have better heat transfer coefficients from convective heat transfer. So what we're going to do is we're going to measure temperature drop and flow rate, and we're going to combine that along with some physical properties of the fluids. Now, you might say, well, what difference does a fluid make? Well, it could be water, could be a mixture of water and antifreeze. And as you change the temperature of any of those fluids, you are changing physical properties that do affect both the hydraulic performance and also the thermal performance of the circuit. And certainly when you start mixing in antifreeze like propylene glycol, you're changing specific heat, you're changing density, you're changing viscosity, and all those have a bearing on the performance as well. So what's a practical way to get reasonably accurate temperatures? I tend to like meters like this Fluke dual channel thermocouple meter. I looked up the price a couple weeks ago. They're running about $450 now. You might find them on eBay or someplace that might run a little bit less, but new, they run about $450. And you see the two thermocouples that they come with up there. These will resolve to about 1/10 of a degree Fahrenheit. You can actually set the meter up very easily. If you look at the buttons on the meter there, actually this button right here, you can read channel 1, channel 2, or you can read the difference between channel 1 and channel 2. They respond fast. The thermocouple is actually that tiny little bead at the end of the cable. So it's very low thermal mass. You can just put this between your fingers and it'll change temperature 10 degrees in a couple seconds. So it's nice in that respect that changes in temperature of the system are, you're not waiting for the thermal mass of the sensor to catch up with the temperature changes in the system. And as far as mounting, here's a 1-inch copper pipe. So I'm just holding that end of the thermocouple against the outside of the pipe. So we don't actually have to, drill a hole in the pipe, put the sensor in there, or install a well. When you have a copper pipe like this, the temperature gradient across the copper wall of that pipe is extremely small, literally perhaps 1/100th of a degree Fahrenheit or less. So that error is really pretty minimal. But we take some decent electrical tape, we wrap it a couple times so it's in good contact with the surface of the pipe, and then I like to put some insulation over it. It could be a piece of insulation tape or just a piece of elastomeric foam insulation. What you're trying to do here is isolate the sensor from surrounding air temperature. So the reading that you're getting is as close as practically possible to the water temperature in the system. And you're going to, for a delta T or a temperature difference, you're going to mount 2 of these. And ideally, you should mount them in the same manner. So if you mount one, you mount it with tape, you put some insulation over it, do the same thing for the other. Because what you're trying to get is the difference between the two. So if there's a slight absolute error just due to, let's say, the conductivity of the tube wall, as long as both sensors have that same absolute error, when you take the difference between those two temperatures, that error essentially cancels out. So try to mount the sensors in identical manners. Now, flow has always been the challenge. Somebody might say, how am I supposed to get the flow rate in a hydronic circuit? Do I have to cut it open, install a flow meter? Do I have to do something else? Do I have to cut the pipe and time a bucket? How fast does it fill? And obviously, that's impractical. It's possible to do that, but it's very impractical. It's expensive. It takes up a lot of time. Now, there are devices like this. These are some of the Caleffi balancing valves. They'll get you in the ballpark, but if you look at their spec sheets, depending on the product, they're rated anywhere from about 10 to 15%, plus or minus 10 to 15% accuracy of whatever the reading is on the valve. The quick setter over on the left, you basically pull the ring out, and the little pointer or the little ball will move inside the envelope there and give you the flow rate. The other balancing valve, you need to have a manometer, connect the thermometer to the 2 pressure ports there, get a differential pressure, convert that over to a flow rate. Another way to get a ballpark on flow, many of the new circulators today with the electronically commutated motors, some of them have a direct readout right on the surface of the circulator. This one right here, the Takeo circulator that has a Bluetooth output. I think some of the Xylem circulators have that now. In fact, I think Grenfus has gone over to a Bluetooth output as well. So you can have an app on your phone and it will tell you a ballpark of what the flow rate is. Now, I actually talked to one of the manufacturers because I wanted to get an idea, what kind of accuracy are they claiming? And one manufacturer suggests plus or minus 5%, but with some caveats here. One is that it's a new circulator, doesn't have any oxides or debris, anything that's inhibiting the rotor that would tend to cause the motor to draw a slightly higher amperage. The flow rates are based on water, not on mixtures of water and antifreeze, so that is going to have an effect on it. And I'm not sure I understand the exact physics of this, but they also stress that the operating point is to the left of the maximum hydraulic efficiency. Maximum hydraulic efficiency is typically about halfway across the pump curve. So we're looking at that left-hand half of the pump curve. As long as you're in that range and these other conditions hold true, they feel that plus or minus 5% is a reasonable accuracy. Again, that will get you in the ballpark, but there are other ways that we're going to talk about here that will get you better accuracy. And this is one that I think is pretty interesting. I've, over the last couple of years, worked with another engineer on some projects doing some data acquisition, and he introduced me to this company, Keyence. It's a Japanese company. They make a wide variety of industrial instrumentation, but they make a small portable ultrasonic flow meter. And the way this works, if you look at that middle photo there, It comes with a small stainless steel fixture, and you can mount this. You basically split that in half. You saddle it around the pipe, and there's 4 screws. You've got a small little cordless screwdriver. You can mount this literally in about 30 seconds. And then the actual electronic package just snaps into that. And the way an ultrasonic meter works, kind of a very basic explanation, basically bounces a signal between 2 sensors. In one instant, that signal is going from an upstream sensor to a downstream sensor. So it's actually going to time in microseconds the timing from when that pulse was created at this sensor. It passes through the tube wall, it bounces off the inner wall, comes back to another sensor. That time is recorded. And then the direction of that pulse is reversed. And the same thing holds true. It's going to time from, in this case, the downstream sensor off the reflection point back to the upstream sensor. There's a slight difference in those 2 times that is directly correlated to the speed of the fluid. And from their data, they can use these meters with different fluids. They can use these meters on different types of pipe. So whether it's copper pipe or a PVC pipe, PEX pipe. And they're claiming a plus or minus 3% accuracy. And I've watched one of these work, and these have error detection routines. For example, if you happen to mount this where there's turbulent flow, it'll tell you that. It'll tell you it just can't take a reading under the current conditions. So it's a pretty intelligent meter, and I think the price is very affordable, especially considering this as a professional tool. If you go directly to their dealers, depending on the size of the unit, they can run $800 or $900, but they're actually on eBay anywhere from, I'll say, low 300 up to maybe $500, and they're brand new. So you'll see this one up here comes with that fixture, comes with instructions. These require a 12-volt DC power supply, so one of those little black box transformers. And they're actually capable of reading a lot of things. They can give you instantaneous flow. They can totalize flow over a given time. They actually have a temperature sensor built in, so they can get one temperature. And if you buy an extra sensor, they can actually function as a direct BTU meter, where they're going to measure flow rate and delta T instantaneously and do that repeatedly and then integrate the total. So it's a pretty cool little device. And as I say, when we compare this to the price of other instrumentations like flue gas analyzers or equipment for charging refrigerant and so forth, even a $400 or $500 price point is good. And keep in mind, this is extremely portable. I mean, you could leave it on a system, but that's not really the idea. The idea is a tool. You're going to put it on, you're going to get your readings, you're going to take it off and use it on the next job and so forth. So one of the questions we had here is, have you ever worked with an ultrasonic flow meter? They've been around for a while. They've been quite a bit more expensive, but like many things, they're coming down to a point where a hydronics professional could afford to put one of these in a toolbox. So Max, I'll let you run that poll. We'll take a look at the results.
So I've got it launched here. I've got a question for you, John. I've got an important technical detail that somebody wanted to clear up. We had a comment that it's actually a 55 Chevy in the photo. Is there any potential that it's a 55 instead of a 57?
I stand corrected.
That was when we sent the hard copies, we got that response back, and I just noticed when we saw the picture at the beginning. So
kudos to the person who put that point in there. That is
a sharp eye for cars for that person. So we'll see if we can find the VIN number and get back about that one. But, okay, so I'm going to end this and share the results. We had a 25% yes and a 75% no.
Okay. Well, in looking at the makeup of the audience, I saw we had a lot of engineers, and I assume some of those engineers have been involved with doing monitoring of systems, and typically that capacity would use something like this. But again, in talking about this relatively low cost ultrasonic meter with relatively good accuracy, I've seen a lot of interest in that meter. So again, check them out. Keyence is the name. You could check them out on eBay or just Google it and take a look at those meters. Okay, let's keep going. Now, again, we're going to take a delta T, we're going to take a flow rate, but one of the constraints in doing that, if you're trying to get accurate results, is we'd like the system to be at steady state operation when we do that. And that's a challenge because most hydronic systems don't spend much time at steady state, especially systems that, for example, might have oversized heat sources. They're going to turn on as they warm up, they're going through a transient. And as soon as that thermostat is satisfied, they're going to cool down. So they tend to spend a lot of time going through this, what I'll call transient operation. This graph, though, shows what the challenge is. If you have a very low thermal mass system, maybe you have a short piping circuit, small diameter pipe, doesn't have a lot of fluid in it, might be fin tube baseboard, again, not a lot of thermal mass there. That might reach a steady state condition in 10 or 15 minutes. But as we go to different configurations of the circuit, maybe it's larger pipe size, it's a longer circuit, so it's going to have more fluid. If it has a cast iron radiator or something else that has more metal in it, that's going to perhaps be an hour or more to reach a steady state. And you'll see how we deal with this shortly. And then the worst one, the green curve there, would be a concrete floor slab, especially from a cold start. It could take literally days to come up to a steady state condition. And obviously you don't want to stay at the site for 24 hours or more to try to wait for that system to be at steady state and then take what I'll call a snapshot, which is the flow rate, the temperature difference, and then proceed to some calculations. So the important thing to realize here is we don't necessarily have to take that circuit up to its normal operating temperature in order to take a flow rate and a delta T measurement. Now, at first, that probably seems wrong, but we're going to basically get a data point, and we're going to extrapolate that data point based on a theoretical relationship between supply temperature, room temperature, and heat output. So to get that line that would give us the heat output at a given difference between water temperature and air temperature, we actually only need 1 point, because 1 point we already have. At 0 delta T, we have 0 heat output. And the theoretical relationship is a straight line. So if we know 0, 0, that point is on the line. We only need one other point to define that line. And we can achieve steady state conditions much faster if we don't have to take that circuit all the way up to its normal temperature. And I'm inferring here we're talking about circuits that operate at relatively high water temperature, like 180 plus degrees. So the guideline that I'm suggesting is to take the circuit to about 20 to 25 degrees Fahrenheit above the room temperature. We do have to get enough difference between the water temperature in the circuit and the room air temperature to drive some heat out of the circuit. And as I'll show you, we have a way to control that. But let's say you arrive, everything's at room temperature, maybe 68 degrees, and you're going to do this test. Well, maybe you can start by taking the water temperature up to around 88 or 90 degrees and see how quickly that system comes to a steady state condition, or what I'll call quasi steady state, almost steady state. Again, we're making estimates. We're not trying to nail this to 3 or 4 decimal places. So we need to be relatively close to a steady state condition. Now, one of the things that does make it hard when we're using, let's say, an on-off heat source, maybe it's an oil-fired boiler, for example, they operate on a set point and a differential. And oftentimes they're turning on, they're turning off, and we're getting a cycling. We're getting a temperature variation that's going up and down. And that makes it, in some cases, almost impossible to reach a steady state condition. We're getting that orange curve there. What we'd like is to have that heat source put out a nice steady temperature. But about the only thing we could do in a situation like this, if we're going to try to use the existing boiler or existing heat source, whatever it is, to put heat into the circuit, is to possibly reduce the temperature differential between when it turns on and turns off. In some cases, you can do that with an electric boiler. You can reduce that differential without doing any, damage to it. It becomes more difficult, more of a challenge when we're trying to do it with, let's say, an oil-fired boiler or even a gas-fired boiler. Basically, you're going to be limited to the temperature differential of whatever controller is turning that burner on and off. Excuse me. Now, we'll talk about a way around that in a minute, but let's talk about the calculations. And probably just about everybody watching this have seen or heard about this formula, that BTUs per hour is equal to 500 times flow rate times delta T, or temperature difference. And the thing I want to stress to you about this formula is this is for water. And it's also based on the properties of water at around 60 degrees Fahrenheit. Okay, so again, it will get you in the ballpark. It's a convenient formula when you're trying to make quick, especially mental calculations. But a more accurate version of that formula is this. And instead of 500, you see there's three numbers multiplied here. This 8.01 is just a unit conversion factor. Capital D here is the density of the fluid, and density of any fluid, be it water or a mixture of water and antifreeze, is dependent on temperature. And I'll show you how to find that in just a minute. And then C stands for specific heat, the number of BTUs it takes to raise a pound of this fluid 1 degree Fahrenheit. So think of this as a general formula that applies over a wide range of temperature and over different types of fluids, whereas this one is definitely limited to water, and its accuracy is somewhat limited as you get up to higher temperatures. So these graphs over here on the right, this one plots density. The blue curve is for water, and you can definitely see there's a change in density, a decrease in density as the water heats up. And then I put curves in here for 30% propylene glycol and 50% propylene glycol. You could fit curves or fit equations to this data. Actually, we plotted the data from some equations that you basically generate the equations using a spreadsheet and taking data from a manufacturer. If you're working with a 40% solution, you can interpolate in here. But again, you can see there are differences, and also that everything is temperature dependent. Specific heat is the lower graph. Water is very, very stable with specific heat over a wide range of temperature from 40 all the way to 200. Essentially, we can treat it as 1 BTU per pound per degree Fahrenheit. That's not the case, though, with mixtures of propylene glycol. So again, the D comes from this chart based on the average temperature in the system, and the C over here comes from the lower chart here, again, based on the average temperature in the system. So let's do an example. Let's put this all together. Here's our system. We've got our dual channel thermometer, thermocouple meter mounted. So we're getting a supply temperature of 120.6. We're getting a return temperature 108.1. I just picked some numbers at random. We've got our ultrasonic meter clamped on that circuit. And actually, it could be anywhere in the circuit. Again, it'll tell you, if you mount it very, very close to an elbow, it might tell you essentially there's turbulent flow, you have to move the meter. Ideally, you'd have some straight pipe upstream of it. But as far as the flow rate, it's the same here, 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 wherever that circuit is. Our ultrasonic meter is giving us 4.2 GPM. And up here it says the system operates with a 30% solution of propylene glycol. So let's start with the average temperature. We just average the temperatures between supply and return. We're at about 114 degrees. So now we can go to these two graphs and we can look up the density. And I did, it's 63.5 pound per cubic foot. Specific heat for the 30% glycol at that 114.935 BTUs per pound per degree Fahrenheit. So we got our D, we got our C. Actually, we have everything. We have supply and return temperature, we have flow rate, and we have the fluid properties. So there's the formula. 8.01, there's our density, 0.935 for our specific heat, flow rate 4.2, and our delta T, the difference between those two temperatures, 24,968. I just rounded off to 25,000 BTUs per hour. So again, this is, this is not, to use an overused phrase, it's not rocket science. It's basically get a delta T, a reasonably accurate delta T, and a reasonably accurate flow rate. Find out what the fluid is, multiply them out, and you get the heat transferability of that circuit. So we got another poll question here related to what we just talked about here. Have you ever measured the heat output of a hydronic component or a circuit by measuring the flow rate and the temperature difference across it and then doing a calculation? Just curious, how many of you have worked with this mathematical combination of these properties and these operating conditions?
So I've got that launched. Another tool that would be good to mention here is a $20 glycol refractometer, because even if you loaded in 50% glycol, if there's a leak and the autofill is open, you may be sitting at 18% glycol now or something. So that's a good one if you're going into test. What you put in 10 years ago may be very different, and that may be an indication that you need to work on something else potentially too.
Yeah, that's a good point. So and the refractometers are very inexpensive, and it's going to tell you what your concentration is.
Okay, let's see. So we're kind of flattened off here. We have a 45% yes, and we have a 55% no.
Okay. Again, I'm just guessing that engineers that are involved with evaluating systems, maybe as an initial aspect of an upgrade or a change in the system, probably have done this type of thing. But for those that haven't, I hope I've convinced you that the instrumentation isn't very expensive relative to other professional quality tools. And the process is pretty simple. Now, I mentioned that when we have a boiler in the system, especially if it's an on-off boiler, it's difficult to get that system to a true steady state condition. So when we were looking at this, we wanted to come up with a way, how could we thermally excite that circuit, which means we're going to put heat into that circuit. How can we do it without using the heat source? What's a simple way to put some heat in there and get away from the cycling of the heat source? And this is what we came up with. This is an apparatus that consists of a few things, and we're going to talk about them individually, but let's talk about where it goes in the circuit. You don't have to get out a hacksaw, and hopefully you'll find that the circulator in the circuit has isolation flanges or ball valves or gate valves on either side of those flanges. We can close that off, remove the circulator, which just 4 bolts, take that out. And our apparatus is made up starting with just some standard circulator flanges. These are baseboard T's. Again, I'm going to show you these components in more detail. Down here, we've got an electric block heater. These are basically just a shell with a heating element and a cord. They're designed to go into vehicles to preheat the coolant in a vehicle in a very cold environment. Try to warm that fluid up before you start the engine. I'm showing an ECM circulator in here, just something that we can use to vary the flow rate. And this little instrumentation up here at the top. And let me just give you a zoomed in view here of what's there. We'll start off just bronze circulator flanges. You can solder in a small segment of tubing here, transition to a baseboard T. That looks like a standard elbow, but it's got a little 1/8 inch FPT threaded side port on it. And you actually can find, you may not find them at the local Ace Hardware or the big box store, but you can buy 1/8 inch ball valves. You can buy these little fittings that'll transition over to an 1/8 inch barbed fitting. You could use some fuel line for this. And what you're trying to do is get up to this T and put a pressure gauge on there. And you'll see it's symmetrical. You do it on both sides. So what this is useful for is to capture differential pressure across where the circulator flanges are. Now, we don't actually have to have that for a thermal assessment of the circuit, but what's nice about this is that you can capture that pressure differential across the circuit at different flow rates, and you can use those data points to actually create what's called the system or the circuit head loss curve. And that circuit head loss curve can then be used to evaluate, what if I change the circulator? What if I take out, maybe it's a 007 and I want to put a 007E in there and run it at a lower speed? You can guess at it, but this is a way to characterize the hydraulics of the circuit, and it's relatively inexpensive to put that together. So let me go to another slide. So that's what that block heater looks like. And again, these run about $70 or $80. As I said, there's not a lot to them. They're some type of a polymer shell. Usually you see the line cord on it. Basically, it's just set up to have a radiator hose connect to it. That's going to be your heat source. Now, to know how much heat we're putting in, we're going to use this little kilowatt meter. You can buy these. They're $25, $30. They're relatively accurate for what we're doing here. And to control the electrical power going to that element, this is a 2000 watt rated solid state dimmer. And I do want to call attention to the order that these in. We go through the dimmer first, and then we go through the kilowatt meter. These dimmers are about 99% efficient, which means about 1% of the power coming into them is actually going to be dissipated through the heat sink back here. That's pretty good. But if we flip that order around, that's power that's being dissipated not by the hydronic circuit, but just being dissipated by the control device. So go through the dimmer first, then you can wire that to a receptacle. The kilowatt meter here just plugs into a receptacle. You can plug the line cord into that. These typically 1500 watt is enough for what we're doing. Here's our thermocouple, dual thermocouple meter, and there's our ultrasonic flow meter. So here's an apparatus, again, that's fairly easy to build, fairly inexpensive, and it's portable. Once you're done with it, you close the isolation flanges, you put the circulator back in and restore normal operation. Okay. Here's one that Bob made up just as we were talking, early on about this. You can see there's the kilowatt meter, the dimmer. Here's the circulator. Here's the block heater. Here's a pressure gauge to that and a couple ball valves. So you open one ball valve at a time. So you get pressure on one side and then close it, open up the other one, and then take the difference in the readings. Okay. So again, same picture, just showing you that that's one physical way to put it together. Now, preparing for the test. Let's say we got a 4-zone system, okay? Before we mount this test apparatus, what we want to do is we're going to take an assessment of the nominal flow rate that each of these circuits operates at. So we want to find what is that circuit operating at as is, okay? So the conservative way to do that is to turn on all the zone circulators. And the reason you want them all on, you want maximum flow rate through the common piping down here, because that's going to create more head loss. And that is going to tend to make the flow rate through the individual circuits a little bit lower than they would be if they were operating one at a time, or just operating independently, completely independently of each other. If you've got good hydraulic separation in the system, like a cast iron boiler, relatively short header, the difference should be small, but we're erring on the conservative side. Turn them all on and then move the ultrasonic meter from one circuit to another and get that as found flow rate. So here's just a list of zones. Here's just some numbers that represent the as found flow rate in gallons per minute. The reason we want that as found flow rate is when we actually put the test apparatus in, we want to set that flow rate pretty close to that as found condition, because that is the condition that circuit operates at. If we were to find an as found flow rate of, let's say, 4.5 GPM, and then we test the circuit at 9 GPM, we're in a sense, we're operating at a condition that isn't going to be present when we restore the system to normal operation. So we're probably going to slightly overestimate its heat transfer because we have a higher flow rate. So we want to be pretty close to what that as found flow rate is when we do the test. Now we're going to mount the apparatus. It's the same picture as before. We're going to turn on the circulator, and it says establish a flow rate approximately equal to that as found flow rate. So you're just going to basically adjust the speed here. You could do it with a valve. You could do a little throttling over here. But with an ECM circulator, many of them have a pretty wide range of speed adjustment. And you've got a flow meter so that you can dial, you can watch the flow rate that you're getting. We're going to put in we're going to plug in the block heater, and I just arbitrarily said, tune it up to 500 watts. That's about 1700 BTUs per hour power input. We're putting a little bit of heat into the circuit just to see what's going to happen. Allow the circuit to stabilize to a steady state. Hopefully that will occur fast. We're not putting a lot of heat into that circuit, so we're not trying to take everything from room temperature up to, for example, 180 degrees. Measure supply and return temperatures. And if you're not seeing much of a differential, crank up the power a little bit. And as I said, go to about 20 to 25 degree temperature above room temperature. Now you're putting enough heat in that you should start to see a measurable differential across the circuit. Okay. Again, we want that circuit to stabilize. So watch the temperature readings, watch the delta T, and as you approach, in theory, you may not get to a perfect steady state condition, but if you're seeing temperatures that are stable within 1/10 of a degree for maybe 30 seconds or a minute, you're close enough. You're going to take your snapshot right there. So you're going to record supply temperature return, whatever the room temperature is, where those heat emitters are, because that is going to affect the output of the circuit, and the flow rate. Now, there's another thing we've got to talk about, and that is the heat source. This could represent, for example, a cast iron boiler. Remember, we're not running this to put heat into the circuit now. We're using this to put heat into the circuit. So what happens is this becomes a heat dissipator that under normal operation would not be a heat dissipator. It would be a heat injector. So if we take water into an off boiler, we're going to warm up the sections. We're going to warm up the jacket. We're going to create some convection currents where room air is going to be drawn in, and it's going to warm up in the heat exchanger of the boiler and go out the exhaust system. It's actually cooling the fluid. Now that condition would not be there. So if we just ignore it, we're actually going to overestimate the ability of the circuit to release heat at a given operating condition, because in a sense, the heat source is acting as another heat emitter in the system or in the circuit. So we need to take some more measurements, and I'll show you how to do that. Basically, we're just going to move our thermocouples and get a T in and a T out on our heat source and account for that. So anytime you know the wattage going into your block heater, you can convert that wattage, just multiply it by 3.413. That'll give you BTUs per hour. Okay. Now, here's a situation with those off heat sources. This is the one that's more concerning. A large, especially cast iron boiler, a dry base boiler. It could be copper tube boiler. But if we're directly flowing through our boiler, is that part of the circuit? These little arrows here just represent heat loss. So we're going to measure T in and T out, and we're simply going to subtract that in our calculation when we do it. And I'll show you that in a minute. If it's a modcon and it's piped in primary, secondary like this, in theory, there should be very little flow going through here if this circulator is off. You can even close the flange on this if you want to make sure there's no flow. If it's something like this, I don't feel it's necessary to take that delta T across here because you should have extremely little, if any, flow going through there. And if you simply close the flange, you're not going to have any flow. So this one is more of an issue compared to this. Now, the heat loss through the heat source that's off, if we know T in and T out, here's T in, here's T out, we know the flow, we know the properties of the fluid. It's the same equation. It's just being applied to this as a heat dissipator. And mathematically, we can work that out pretty simply. If we know the delta T of the circuit, okay, that would be the temperature readings we're taking on our test apparatus where the circulator was. We just subtract the delta T of that inactive heat source from that. That should be small. That might be 1 or 2/10 of a degree Fahrenheit. Okay, it should be relatively small compared to the ability of the circuit to dump heat through the normal heat emitters. But again, the net effect here is we're trying to improve our accuracy by not including heat that's being dissipated by a heat source that's offline. So that's our equation. And then finally, you've got to keep your numbers organized. So again, I made up some numbers here, a 4-zone system. These were our initial existing flow rates when we turned all those pumps on and we just went from one circuit to the next and measured flows. Okay. Here's the flow rates we established during the test. And again, we're trying to essentially establish the same flow rate. Doesn't have to be exact, but it should be close. Here's some input powers that we've read on our kilowatt meter. We've converted that over to BTUs per hour for each zone here. Here's our supply temperature for each zone when it was being tested. Here's a return. Here's the room air temperature. And again, different rooms may have different temperatures. This was our inactive heat source in and inactive heat source out. You could see I've tried to keep these numbers pretty small because they should be small. But that's that delta T that we're going to have to subtract. And let me just go back. We're going to use that equation right there. We've got all the data we need now to calculate what is the net heat output of that circuit. Okay. And then the final thing that comes into play here, let's start with this graph. This is, it says approximate heat output of the circuit versus the difference between the supply water temperature and the room air temperature. This relationship right here, this is one of two formulas that is the basis for outdoor reset control. And that symbol means approximately equal to. The linearity of this depends on what the heat emitter is. If it's a fan coil or a radiant circuit, it's a very, very good linear relationship. As you start to get more convective output, the numbers vary a little bit more. But again, the word estimate here is important, or it's the estimate we're going to get from using this is close enough. So back to the graph. We know that if we have zero difference between supply temperature and air temperature, in other words, let's say the air temperature around the circuit is 70 degrees and we put 70-degree water in the circuit, we have 0 delta T. We're going to have 0 output. So we already know that point. And for each circuit, we've just found a point somewhere else on this line. It might be here, it might be here, but all we need is one point, and then we just draw a line through it. And that now becomes your estimating tool for what is the circuit capable of at other supply temperatures. And you could use the graph if you make the graph, or you just find the value of this constant K, and you can do that from your data point. For example, if I tested a circuit and I found I had 15,500 BTUs per hour, and I had a fluid supply temperature of 125 degrees, the room was 68 degrees, and I want to figure out what this K is, well, I just rearrange the equation, solve it. There's the value of K. Now, that number is now, think of it as the fingerprint of that circuit. It's specific to that circuit, whatever nuances are present in that circuit. So if I want to use that formula at some other condition, for example, let's say I want to bring the supply temperature down to 105, and I want the room temperature to assume to be at 70. Well, the K value isn't going to change, but the two temperatures changed. So now we're getting 9,517 BTUs per hour. And that's kind of the end of the thermal evaluation of the circuit. You could put all this in a spreadsheet. I like to do that. It makes those calculations essentially instantaneous. Going out, obviously you have to be on site. You have to take these measurements, and you have to keep that data organized. You don't necessarily have to enter it into a spreadsheet right on site, but make up a table. Let me go back, something like this, so you get all the data you need. You know, the thing you don't want to do is go on site and say, oh, I forgot the room temperature, or I forgot to get the, that temperature drop across that inactive boiler. So, by making up some kind of a table and knowing you have to fill in certain cells in that table when you're on site, that just minimizes, the chance that you're not going to get the data you need. So I just took this data here and I applied that previous equation. The density of the fluid, really, for these average temperatures that we got the circuit up to, you can see they're all in that mid 80 degree range. So the fluid properties really did not change to a degree that is going to make much of a difference in the calculation. So these numbers are all the same. In theory, yes, the density changed very, very slightly between 82 and 85 degrees. But to 1 decimal point of accuracy, no, it didn't. Same thing with specific heat here, okay? We're assuming water in the circuit, specific heat of 1, but you can definitely see these circuits had different heat outputs at those conditions. So that's kind of a wrap on it. Let's see, we've got just a few minutes left here. I do want to, actually, I'm going to turn this back over to either Max or Bob, whoever would like to just take us through these, and then maybe we have time for a couple questions.
Sure. So and for some reason the slides came over with a black background here, but it looks like we can see the info. So if you have any project specific questions, you can call us and you'll get a human being will answer the phone, one of the team members there. Or you can send us questions to the techsupport.us@caleffi.com email address. Sometimes these spin off into a specific job site that's easier to follow up by phone. So let us know if we can help there. And then we had a question that I think you kind of covered in the last slide a little bit, but if you were working with something that was on an outdoor air temperature reset with a system, would you recommend to just kind of flatten that curve out, maybe to just set like the bottom?
Yeah, well,
or something.
If you're going to try to use that heat source as the heat input for the circuit for the test, ideally you want it at a nice steady state temperature. So anything you can do depending on what the heat source is to, flatten that reset line out and just get a temperature. Remember, it doesn't have to be an exact specific temperature. You're trying to get that circuit up roughly 20 to 25 degrees above room temperature, but the more important aspect is you're trying to steady state that circuit. So flatten the reset out, or simply turn off that heat source, use the electric heater. And the nice thing about that electric block heater is it's stable.
Yep.
An electric heat source with a given wattage going into it is going to be about as stable as anything. So.
Okay. Yep. That's perfect. And then let's see, a lot of other people just signing off here. So I did put in the meeting chat in I forget what they call it, the Q&A or the chat for attendees, links to Hydronics 35 as well. So if you want to follow along, that's kind of the textbook that the slides came out of basically for this presentation. So that has more of the details. Also, when you exit the webinar, if you want a copy of the presentation, you can click yes there and you'll be on the list that will send those out. Let's see what else we've got here. Bob, did you have any other questions that you wanted to add as well that you saw come through the chat?
There was one about if it was a primary secondary piping. Obviously, you'd still want to run all the zone pumps to get that total fluid GPM of the system. Really, the piping wouldn't matter that much if they're parallel circuits or a primary secondary zone pump. There you go.
Yeah, that's a good one.
Yeah. Right. I'm assuming that what they mean by primary, secondary, is something like this, where.
Yeah, that's what I'm assuming too. Is if you had multiple pumps off of that primary loop, you'd want to run them all to get your total GPM. So.
Correct. Run them all because again, that gives you the lowest flow rate. And what you're basically simulating is design load or an assumed design load where all the zones would be on. And you'd have the maximum flow. In this case, it would be just through these T's. Yep. Or if it was a hydraulic separator, it would be just through the hydraulic separator. That should be relatively small, but with all the zone circulators on, you're going to get the maximum head loss here and the minimum flow rate, which is the conservative operating condition to evaluate its output.
Yep. One more maybe. How is the specific heat calculation modified to different percentages of glycol? And I see you just made that graph at that one.
Yep. Yeah, there's just a backstory behind these graphs. You can go to antifreeze suppliers like Dow, Chemfax is a Canadian one, and they publish detailed properties for their fluids at different concentrations and different temperatures. So what I did here, I just took one of those. I think it was for Dow Frost, and I just used the data to generate these curves. So you can find this information, or these curves are. I consider them generic enough that they can be used for that data too.
Yeah, you could use that for any brand basically on the different percentages there, and these again are
within the accuracy that this whole procedure is going to generate. I think you'd be fine using these curves regardless of what the brand of the antifreeze was.
Okay, and then somebody asked about using the.
I've got another one that I saw as you were doing that one. So this question is, can you compare the thermal performance in BTUs per hour, that number, to the BTU output of the boiler be of any value? So that we had a contractor when I was a rep who went out to the gas meter, turned the boiler up to 100% fire, and then clocked the gas meter to see how many units of gas came through at that rate. And it was not the same as the boiler, but there's
no, because of the efficiency of the boiler would have to be the difference between them. But I think maybe I'm reading it a little bit into that question. You could use the flow meter and the delta T, the dual temperature thermometer, to certainly evaluate what the boiler is doing. If you know the flow and you know the delta T and the fluid going through the boiler, it's just this equation here minus, it's just that equation right there. T in, T out times the fluids times the constant and the flow rate, and you've got BTUs per hour in the boiler. So that's another, I guess you'd call it a spin-off. If you have one of these ultrasonic flow meters in your toolbox, you can quickly verify what that boiler is doing, even if you're not interested in evaluating individual circuits within the system.
One of the things that we found in doing that as well with other projects when I was a boiler rep. The amount of energy in a unit of gas, of propane or natural gas from your supplier, there's a pretty big variance in that. That
Mhm.
if you're out
Yeah.
in the middle of nowhere, you're even just truck to truck, you might have a little bit of a BTU difference there. So you could clock your gas
Yeah.
meter and sit out there with a stopwatch on a bucket for a week, and then do that 2 weeks later and get a different number there. So again, I think kind of to what you said about the glycol, probably within a rounding error that it wouldn't be
Yeah.
worth the time to do it.
Yeah.
That you be a
Yeah.
percentage
Yeah.
off.
The whole incentive for doing this type of testing is to give a reasonable estimate of what the circuit, or multiple circuits, what that system is capable of if we use a different water temperature, which is likely, especially if we're going to go over to a heat pump. Um, so it hopefully is a way to answer by doing some calculations and doing some measurements. You're not guessing at what that distribution system is capable of when you perhaps put that heat pump into that system. You know, the alternative is to cross your fingers, cut the boiler out, put the heat pump in, right? That's just not professional. So, we wanted to give a reasonably accurate method. And again, I want to stress, we hope that you'll find this is a practical approach. This is not a $20,000 piece of equipment to go in there. It's something that's affordable. It's something you can build in your shop and use it over and over again.
I've got another one that I'm just typing in the response as well. I can just send this to everybody in the webinar. To discuss solutions to modify the distribution system by adding baseboard or radiators or something. And I'm going to send a link to the lowering water temperature in hydronic systems,
Yes.
hydronics issue. That's really a great place to evaluate how, like, okay, we did this exercise and there's only 8 feet of baseboard in that unit. That's not going to work for 120
Yeah.
degree supply temperature. What do I do now?
Absolutely. And I think that's number 25, if I remember right, Max, issue
It is.
25
Yep.
of Hydronic. If you're finding that at a lower temperature, you simply don't have enough output to match the load, what do you do? And essentially that comes down to two things, which is covered not only in Hydronics 25, but it is in the YouTube of one of the coffee with Caleffis we did. I forgot, it was probably 4 or 5 years ago now, but two things you can do. You can improve the thermal envelope of the building, which will bring the temperature requirement of the water down because you're reducing the load, or you can add heat emitters. And we talk about both options in Hydronics 25, as well as the Coffee with Caleffi recording.
And just as an energy conscious consumer, the best answer is probably blowing some more insulation into the attic, as much as we'd love to sell hydronics.
Very well could be. It depends what your starting point is.
And an energy audit can be good for that too, just a third party to come in and say, yeah, here's where all the energy is going straight up into the attic. So start with that, and then maybe you won't need as much of an upgrade with the radiation.
Yeah, and again, that may take you to a weatherization specialist, a blower door, and a thermal camera, to find out what's going on, and then evaluate what are your options as far as weatherization. If you've got 4 inches of fiberglass in an attic in Caribou, Maine, you're definitely more cost effective to deal with it from adding more insulation than trying to just add heat emitters.
Well, I think that kind of takes us through the questions, unless you can see any other ones. We can probably close it out there. And then we've got a couple that will follow up by email after the webinar. But yeah, thanks again, John. It's always very helpful to figure out the best way to use the energy wherever you are, whatever the heat emitter is, whatever the energy source, and the fuel, to make sure we know where it's going and if we're losing a lot of it. So great topic. And we'll be back next month with Saeed from Rayhow. I used to work with him as a trainer for a bunch of years, and we've done that presentation together a few different times. We'll go through radiant systems and then also some balancing options there. So we'll see you next month, and thanks again for attending. Thanks, John.
Thank you, guys.